that is your gamma is not mu, then Z will be the ratio of mu by gamma. Understood? If your gate is not symmetric, then naturally your pull-up to pull-down ratio will differ from the standard CMOS gate. In that case, your Z will have a value. Otherwise, if you are taking the symmetric gate itself, then Z will be a value of 1. Understood? Has everybody understood? You can understand template gate in that form. So because template is something which is, because we are already saying there is a standard gate. Then what do we mean by template? Okay. So it is, suppose I am taking a NAND gate. So NAND gate which is designed to have the same drive capability of pull up and pull down as that of a test. That means we can take now into account a gate which is not symmetric. Then I will have a Z value which is other than 1. Then the Z value will be other than 1. Got it? Clear? So if you are already taking a standard gate, your template is also a symmetric gate, and your gate is also symmetric gate, then Z automatically becomes 1. Okay. So far, now we will move on to applying logical effort to other logical families like the pseudo NMOS. We start with pseudo NMOS because it has very similar structure as that of a standard CMOS. So, sorry, static CMOS. It has a very similar structure. So we are deviating, but we are deviating in a manner in which it is easy for us to develop the relations. It is easy for us to develop the relations. So we start moving now into the pseudo NMOS. Now pseudo NMOS, how do you differ it with the static CMOS? Input does not go to both pull up and pull down. Okay, so we have a pull up separate which is always on, and pull down input goes to only pull down block. So if you have such a condition, then I can design my all other parameters, they remain the same. All the relations for D, D minimum, best stage effort, all these expressions they don't change. But I should now know how to compute the G for such a relation. The logical effort for such a relation, which is slightly, it has to be done in a different manner. And as we know, G is actually nothing but an indication of the ratio of the drive capability. So how bad is your gate in terms of drive capability in comparison to standard? That is actually your G value. So when we reflect it in terms of input capacitance, because input is also dependent on W by A. Okay, so when we reflect it in terms of the C in, we capture that in. Because W by S, they also come into the C ratio. And when you are designing in the ratio of mobility, then mu effect also comes into the W. Then the mu effect also comes, the W gets enhanced. The W gets enhanced, so that also gets captured into the C value, C in value of the gate. So that is why you can have two methods of defining the G. That is, express it in terms of the drive capability of the gate with respect to the drive capability of the standard. Or express it in terms of the input capacitances of the two gates. Everybody understands that? Okay. So now when we come to the logic families, the first one we are taking is a pseudo NMOS. And pseudo NMOS, as we know that the pull-up path is always in an on state. It keeps on charging. So whenever you want the node to discharge, we have to make the pull-down path strong. We have to make the pull-down path strong. That is why normally, if my static CMOS, the ratio for pull-up to pull-down is 2:1, it is actually the reverse in the case of pseudo NMOS. It becomes 1:4. It becomes 1:4. You understanding what I am saying? It is not 2:1. 2:1 I am taking in terms of pull-up to pull-down. So in the static CMOS, pull-up has a larger W. Whereas in the case of a pseudo NMOS, because we have to make pull-down stronger, we give it a larger W. So it becomes actually 1:4. Pull-down has a larger W in comparison to pull-down. I am taking 1:4. You may argue, madam, I will take to 3.5. Okay. That is again one example that I am taking where we are designing in the ratio of 1:4. A pseudo gate is designed in the ratio of 1:4. You may differ. You may differ accordingly. Calculate all your relations. Okay. So we are designing a pseudo gate in the ratio of 1:4. And now how to get this 1:4? Now you can choose your own values. We are assuming that mu is 2. Mobility is still 2. But my W ratios are in the ratio of 1:4. It is writing as 4:1. It is actually pulled down to. It is actually pulled down to. So that current is in the ratio of 4:1. Pull down to pull up, not the pull up to pull down. Okay. Be very careful. So now he has taken in the book. He has taken the ratio as 2/3, 4/3. It is not a standard. You can choose your own. But let us understand how this ratio helps him in getting the functionality which is desired. Accordingly, you can adapt your own gate. Okay. Now, what is he doing? That he is making it as 4/3. My standard CMOS inverter is still 2:1. Remember that. But here we are designing in the ratio of 1:4. 1:2. So I want the drive capability as 1 for the pull up and for the pull down to be 4 times. To be the 4 times. Drive capability of pull down block to be the 4 times. So he has taken it as 2/3 and 4/3, assuming that mobility for PMOS is half of mobility of NMOS. So if I assume mu to be 1 here, then the current for this pull down will be 1 mu into W by L proportional. It will be mu into W by L proportional. So mu is 1, W by L is 4/3. So current will be proportional to 4/3. Current here will be proportional. Current of this transistor will be proportional to 4/3. Okay. Let us look at pull up. Mu is half. Mu is half here, and the sizing is taken as 2/3. So the current will be proportional to 1/3. So current through this transistor will be proportional to 1/3. Clear? Current through this transistor will be proportional to 4/3. Clear? Now, because this is always in an on state, it keeps on charging this with a current of proportional to 1/3 units. As a result, this keeps on discharging it with a 4/3. As a result, the net pull down rate will be 4/3 minus 1/3. Net pull down rate will happen at the rate of 4/3 minus 1/3. It will not happen at the rate of 4/3. Pull down will happen at the rate of 4/3 minus 1/3. That is 3/3. That is 1. So actual pull down capability is 1. And pull up is how much? 1/3. So actual pull up current is 1/3 and actual pull down current is actual pull down current is 1. Everybody understands that? So why this ratio has been chosen as an example? So that you can show that pull down current is stronger than the pull up. Pull down current is stronger than the pull up, and then if you design an inverter, it is easy for you to design an AND gate, easy for you to design an OR gate. Okay, because it is simply now keep on following. Pull up will not change anywhere. Whereas pull down, you want this to be 4/3. So actually, for a series, it will become 8/3, 8/3. For a parallel, it will remain as 4/3. It becomes easier once you design a basic NOT gate. Okay. So now let us look at how do we get a 4:1 ratio. How do we get actually the 4:1 ratio? Because pull-up current is 1:3. Now it is, I am saying there are now two different things. Earlier, there are now two different things. One is the transistor current. Other is the pull-up or pull-down current. And here they are different. Here they differ. Because your transistor current is 4/3, but pull-down is happening at a rate of 1. Are you getting? Pull down is happening at a here. These are two different things. It is not the same. Pull down current is not same as the NMOS transistor current. It is not same as the NMOS transistor current. So if I look at the pull up to pull down or I discharge to I charge, that ratio is 3. But if you look at the transistor current, that ratio is 4:1. If you want this to be 4:1, then change. So with 2/3 and 4/3, I am getting a pull up to pull down ratio of 1:3. It's not 1:4. This is point to be noted. Because your choice is such 2/3 and 4/3. Your choice is such. If I desire a 1:4, I should have taken another value. Can you give me one value which can lead to 1:4 pull up to pull down? One choice of values for which the pull down to pull up is 4:1, or discharge to charge ratio is 4:1. Here it is 3:1. But transistor ratios are 4:1. Transistors are designed in the ratio of 4:1. That is things to be made clear in your mind. Anybody, Goa campus also you can design a particular combination which can lead to a pull down current 4 times the pull up current. Okay, you may try at home. Give it a thought. All of you can do some kind of a brainstorming and try to come up with the values. As I said, these values which has been taken here in the example 2/3 and 1/4, they are not standards. They can be changed as per your wish, as desire, as per your requirements. Okay? But have you understood that how to understand a pseudo NMOS gate? Remember from a static CMOS, okay, I have seen the requirement for an NMOS. Accordingly, I have designed an inverter, which is a pseudo inverter. And from the pseudo inverter, now we can translate all the concepts to any other gate, NAND gate, NOR gate, XOR gate, by using the same principles. So once you know the current capabilities, now we can find out the logical. Now we can find out the logic. Remember, our basic standard is still a static CMOS. Basic standard gate is still a static CMOS. But here drive capabilities are different. And also the way operation is happening is also different. Okay? In the case of pull down, both paths are operating, both paths are conducting. Whereas in the case of pull up, there is no input is there. It is always constant. The pull up is always the same for any other transistor, for any other gate. Pull up path does not change. Pull up path never changes. Okay, and my pull up is 3 times or 1/3 weaker than the pull down. Remember, my pull down is 3 times stronger than pull up. Got it? Okay. So now, as I said, the net rising current is corresponding to 1/3 and net fall current is corresponding to 1 in a pseudo NMOS. So if I look at this static inverter, which is a pseudo NMOS inverter, how do you find its value? If you look at the G down, now I cannot look at GA or GB. Separate. There is no meaning now. I have to look at up and down. I have to look at up and down transitions. Then only I can compare with my static CMOS inverter. So we look at the down current which is controlled by my input. The downfall or the down transition which is controlled by my input. So in that case, the net input capacitance here is corresponding to 4/3. I can immediately compare it with that of static CMOS. Static CMOS both have a net fall current of 1. net pull down current of 1. So I need not multiply with any other factor because my drive capability, pull down drive capability is same for both. So here the net C is 4 by 3 divided by 3 of a static CMOS inverter. G is a ratio of C. G is a ratio of C in. So 4 by 3 divided by 3, it comes out to be 4 by 9. What does it indicate? 4 by 9 is lesser than 1. Remember, for static CMOS, G is 1 whether you have a pull up or you have a pull down. Whereas here, G down is less. Can you justify its lower value? Is there any reason to justify? Why are we getting G down to be less here? G down is coming as less than 1. Why? Yes, because there is C for PMOS is not coming at all. Whereas it is coming in the case of a static CMOS inverter. So that extra loading is missing. That extra thing is missing. So G is becoming less or down transitions. Now we look at the up. Up you cannot compare because in a static CMOS inverter, there is an input going over there. Here we don't have an input, so DC bias given to this. Okay, so we cannot directly compare one with one. So I simply say that going by the fact that my pull down is 3 times stronger. So accordingly, because G is either a ratio of I or a ratio of C in. Okay, so G down is whatever G down you are getting, make it 3 times weaker. For pull up, make it 3 times weaker. Weaker means make it increase. Because G is higher means weaker. Bad. So my pull up is 3 times bad in comparison to pull down. So whatever G down, multiplied by 3. Multiplied by 3 and you get your G up. And you get your G up. So it comes out to be how much? 4 by 3. It comes out to be 4 by 3. And then you can take the average of G up and G down, comes out to be 8 by 9, which is close to 1 but less than 1, simply because it has to be less. Why? Because your PMOS inputs are not going to the PMOS at all. PMOS is a simplified block or pull up is a simplified block. That is getting resulted into the G. Clear? So no series combination in the case of P. It's only series combinations are happening in the pull down. There is no series combination in the P. That is why pseudo NMOS average value G is coming out to be lesser than that of a static CMOS. Okay. So now everything is very, very clear. Can you get the expression for any, say, a 2 input NOR gate? Do you justify these values that I am getting G down and G up? G down and G up. Any one path you can take. It is same as inverter. If you take a NAND gate, then it would be G down means 2 transistors would be participating. Each one will have a, so there can be a G down for every single input, A or B. So every single input will have 8 by 3 divided by 3. G down for A as well as G down for B, both will be the same. They will not change. Because both have to participate, then only G down can happen. And G up will be simply again make it 3 times weaker. Okay. So once you know how to compute the G values, rest all the process remains the same. All other process remains the same. Then simply the path effort, find out the path effort, the best path effort, best stage effort condition, minimum delay condition, use all these values as it is. And then compute or apply logical effort to compute the delay of any pseudo NMOS gate chain. So maybe the same example that we were taking for skewed gates, we can take it here. Just replace every gate by a pseudo gate. Replace every gate by a pseudo gate. Apply all those expressions that we have derived for a static CMOS. Apply it here and then get the expression for your delay. Get the expression for the delay. So it is very easy to translate all the principles that we have developed for static CMOS to pseudo NMOS. We just need to know how to recompute or how to design a way to compute the logical effort values. Because operation is different in both the cases. We have to find out that. Now somebody will say that we have something called a symmetric logic also. Symmetric gate, where you design any gate by using inverters only. We are not following static CMOS. Just use static inverter everywhere in some possible combination. Accordingly do the sizing and let the functionality come. Let the function come. A very simple example is a NOR gate designed by using two inverters. A NOR gate designed by using two inverters, so you have two inputs A and B and there is an output. You want this function. You want this function. 0, 1. This is a NOR. Please check, it's the NOR function. Is it a NOR function? It is not. I want this function. For both 0, 0, 1 and rest all everywhere to 2. So how can you get it? Normal operation is, I could have taken a standard 2:1 inverter, but that will not yield this function. The reason is, if it is 2:1, 2:1, assume. This is 2:1 and this is 2:2. For 0, 0, both PMOSes will be on, both NMOSes will be off. Then this would be charging and this would be charging. I would get a charging output, this one will come. If both are 1, 1, again no problem, both NMOSes will be on. So both will be discharging and finally output will be discharged. But if I take a 0 here and a 1 here, the 0 means this will be charging and a 1 here means this will be discharging because both are designed to have the same drive capability. 2:1 you are designing, as a result, load will not be able to discharge. Because the two currents are back each other. You will not be able to discharge. So I cannot work with 2:1. For symmetric gates, where you are designing only by using inverters, 2:1 will not work. I have to change my ratioing. We have to change the ratio. And we have to change because it is not a 0, 0 combination which is causing a problem. Neither 1, 1. It is a 0, 1 or 1, 0 combination which is causing a problem. So we have to design for 0, 1 and 1, 0. Okay. So in this case, they have chosen the values to be nearly same as pseudo NMOS just to show that it works over here. So how? That if it is taken as a 2/3 and 4/3 and this is also 2/3 and 4/3. We are deviating from mobility ratios. Now static CMOS inverter is now designed in the ratio of 2:1. We are deviating because we want the symmetric logic to work. Okay, so this is 2/3. So when this is 0, 2/3 will be on, this PMOS will be on. When this is 1, this NMOS will be on. So this will mu is half. So current will be proportional to 1/3, this is 4/3. So this current is 3 times stronger than the 1/3 value. As a result, this node will discharge. As a result, the output node will discharge. Do the reverse. Do the reverse. If this is 1 and this is 0, the same thing will happen. So the node will discharge. And for 2/3, when both are on, A and B both 0, 0, no issue. Both nodes will charge and output will automatically charge because NMOSes will be off. And that will be true for 1, 1 combination also when both PMOSes will be off and NMOSes will be. So I will get my function if I do the ratioing in this particular, with this particular choice. That PMOS is 2/3 and NMOS is, then I can design any gate by using only inverters. Only static CMOS inverters, but the care is to be taken how to size. Now your pull up to pull down may not be the mobility ratio because you have to get the function. Functionality has to be obtained. And since all the results that we derive from static CMOS, they can also apply here because it is a kind of a pseudo gate. It is a kind of a pseudo gate.
Ma'am, in this, why is the GD differing for the two combinations?
We will come to it.
Okay.
Let us. This is not a correct value. I will ask you to derive it. Okay, first of all, understand the operation. So this is actually designed by using static CMOS, but giving you a pseudo NMOS kind of an operation. Why am I saying that? Because when discharge is happening at the same time, charging is also there. At the same time, there is a charging current also. It is giving you a kind of a pseudo NMOS operation. But designed with only static CMOS. So you can, this is known as a symmetric logic, not a symmetric gate. This is called as a symmetric logic. You can design any gate in this world by using only static CMOS inverters, but with proper ratio. Okay, so now if I say that both are on, so both are 0, 0, both PMOSes are on. My standard inverter is this. My standard basic gate is this one, designed in the ratio of 2:1. And here they are designed such that their drive currents are same. So I can take both to be equal to the unit. I up is also corresponding to 1, say, and I down is also corresponding to 1. Let me assume that. Okay, they have the same drive. Now if I look at this gate, which is a 2-input NOR gate, I have, if both are 0, 0, the current will be proportional to 1 by 3. This current will be proportional to 1 by 3. This node will be charged with a pull-up current of 2 by 3. It will be charged with a current of 2 by 3. And this is also charging with a current of 1. This is charging with a current of 2 by 3. If you look at the ratio, of the two currents, what G value you should get for up transition? It should be, how do you find? I reference or I standard upon I, the gate, any other gate. Okay, I standard is 1, divide by how much? How much you are getting? 1 by 3 plus 1 by 2, 2 by 3. Divide by 2 by 3. It comes out to be 3 by 3. Naturally, it is more than 1. It has to be more than 1 because there are 2 gates. Each one having a degraded drive capability, but total effect is no. Getting it or not? Okay, so you are getting a total value of how much? How much we are getting? 1.5. G value is 1 more. So total is coming out. No. Each one is having a value of only 1 by 3. 1 by 3. 1/3 of that of my standard. When you add, it becomes 2 by 3. It becomes larger. But even then it is not still matching with 1. The drive capability is not reaching 1. So G is coming out to be high. G should be high. That's what you are getting. G is coming out to be high value. That means a symmetric logic gate for pull-up transition. For 0-0 combination. Your G is a high value. It is bad. This gate is bad in comparison to standard gate. The value comes out to be 3 by 2. Do it for the same process. Do it for 1-1 combination. It is discharging with a current of 1. No. Yes or no? क्या हो गया? Symmetric logic. It is discharging with 4 by 3. It is discharging with 4 by 3. So total discharge current corresponds to 8 by 3. Here it is 1. So how much your G should be? 1 upon 8 by 3, it is 3 by 8. Even lesser. Even lesser, because already you are having a discharge current 4 by 3. Which case? When both have 1 1. Here the discharge current, each discharge current corresponds to 4 by 3. Which case? 1 1. Discharge current is not 4 by 3 when this is 0 and this is 1. Then your discharge current is not 0. Then your discharge current is how much? 4 by 3 minus 1 by 3. It becomes what? It becomes same as the standard inverter. It becomes same as the standard. There you will get the value same as the G equal to 1. Make changes in the table. I hope you all understand, because we have to look at the drive capability ratios of the two gates. How bad or how good is my gate in comparison to standard for pulling up and pulling down the drive. Clear? So I can now, if this example is clear, I can give you any symmetric logic gate. You can find out the G values and then take a path. Take a path of asymmetric logic gates and apply all the principles of the delay minimization, and the number of stages that you want to optimize. All the concepts you can apply to the symmetric logic family. Symmetric logic can be taken as an extension of pseudo. It behaves like a pseudo NMOS gate. So can you see that I'm putting myself, confining myself only to the gate logic, where the inputs they go to the gates of the transistors. We are not looking into the pass transistor logic, because there the input can also go to source and gate. So there is a difference in pass transistor, and because whatever logic which are similar to the static CMOS, we are looking at them. So that is why pseudo NMOS we have taken, symmetric logic we have taken, and then we can go to domino, which is again a gate logic family. So if I look at my gate logic family for a domino CMOS, it's a single stage. You can say domino has an inverter also. Okay. Let me say a dynamic gate, because domino is a combination of dynamic and a static. Okay, so we look at a dynamic gate. As I told you earlier also, the dynamic is nothing but, also domino is nothing but a kind of a skewed gate. It behaves like a skewed. So if it's a dynamic gate which operates with a clock, so there is a pre-charge transistor, there is an evaluation transistor, and we have input going to the NMOS block. So this is one, so this becomes a dynamic inverter. This becomes a dynamic 2-input NAND. This becomes a dynamic 2-input NOR. Like one stage. Okay, and then it's very simple. G, if you look at G pre-charge, pre-charge is same for all. Pre-charge is same for all. And no input is going to for pre-charge. For pre-charge operation, nothing is going to the pull-up block. Inputs are getting retained only in the pull-down. So can you compute? So now if I design, now it need not be 2:1. I need not have a pre-charge to pull down in the ratio of 2:1. It's not necessary. Because for my evaluation, I am only looking at my pull down transitions. Pull up is certainly only for pre-charging. That is actually not giving me a kind of a, you can say I am not interested in looking at the delay of that. Because whenever clock is low, it is a pre-charge phase. And my delay then starts with the clock edge. I start counting my delay with respect to the clock edge. So from clock edge, before it is a pre-charge phase, so that is something different. That does not come into delay. My delay starts with the clock edge. So clock edge till the final pulling down of the node. That is my delay in the case of a domino. So actually the pre-charge phase is something different from, that does not count into the delay calculation. We do not calculate, include it in the delay calculation. Have you understood all this? Okay, now, so my delay is arrival of the clock edge. Okay, so now if it is only pull down I am looking at, so I would be more interested only in looking at the G down. So G down here and a G down here. Okay, and now you can compare with that of a static CMOS gate. Okay, looking at only the A, because it is very, very similar. So it is A, so this is 2 by 3. It is 2 by 3. So there also you have an input, here also you have an input, input to input, compare. There you have 2 inputs, here also you have 2 inputs. Okay, so this becomes 3 by 3, this becomes 2 by 2. Very, very simple. Domino is also, it's very easy to extend the principles of static CMOS logical abort concept to domino. This is dynamic. Now I say I have a domino which is actually a combination of the 2 gates. Dynamic plus static. Static is an inverter. So I should look at my domino gate as a 2-stage gate. It is a 2-stage gate. So my total G will be actually the combination of the G's of 2 stages, which is nothing but, according to my path, it becomes a path of 2 gates. So total G will be G1 into G. G1 into G2. So that is how we find the G value of any domino gate. We compute the G for each and then we multiply them together. Okay, so like here, you can see this is one gate and then followed by a other gate. Now this is H is written. H means high skew. What do you mean by high skew? It is favoring high going transition, because when this goes low, this has to go high. I have to design this gate to be high skewed. I have to design this gate to be high skewed. And this gate to be designed for down transition. Down transition. So I may be putting the value over here. It need not be 2:1. I need not make it as same drive capability as that of the pull down. That is not required. I can make it lesser. I can make this pre-charge unfavorable transition. I can make my pre-charge unfavorable transition so that the down transition is favored. The down transition is favored over it. And in that doing so, I would be increasing my pre-charge delay. Yes. But then remember, in a pre-charge block, there is only a single PMOS. You don't have a series of parallel combinations. So that delay actually in itself is also very small. So even if you make it weaker, the delay will increase. Pre-charge delay will increase, but it's not going to increase by a tremendous value. It's a very simple block. It's one charge transfer over. No series combinations over there. Series combinations are happening only in the pull down, which can cause the delay to increase. Clear? So if it is a domino gate and we have got a dynamic gate followed by a high skew inverter, I will have the total G for this will be, the G for this stage is 2 by 3 and the G for this stage is how much? Remember how do we design it to high skew gate? High skew, it favors high going transition. So pull up should be stronger. So it is, what do? We make unfavored, slash it by half. Unfavored is pull down, slash it by half. So normal 2:1 becomes 2:2. That's what we do for designing a high skew gate. So it becomes 2:2. Okay, so this G up for this comes out to be 2:2, and the G for this comes out to be 2 by 2. As a result, multiply the two together. How do you get this G up as 25 by 30? Or design it in the ratio of 2:2. So get your G up value. Get your G up value. It is designed in the ratio of 2:2. Get the value for G up. No, that is okay. Others, I feel others are not getting the idea. How do you find G up? You make the drive capability, same, then add the capacitances and take the ratio. What is G up here? The drive capability is 2. Mu is also 2. So drive capability with standard in gate is the same. So add the total, 2 plus 0.5, 2.5 divided by 3. That gives you 5 by 6. Got it or not? So this value comes out to be 5 by 6 and 2 by 3 multiply gives you 10 by 8. Again the value is less than 1. It should happen, I know, because there is a pull-up block which is very highly simplified. Which is not so in the case of a static CMOS. You have a complete pull-up block, which is a dual of pull-up. But value is increasing because of 2 stages coming. Value is increasing because of 2 stages coming. Because the total value is the multiplication of the 2 G values. So you can now do it for any other gate. Now this is footless domino. One domino is a footed domino. Other is a footless domino. Other is a footless domino. Footless means you remove evaluation. You remove evaluation pressure. Then G becomes even lesser. G becomes even lesser. It becomes 1 by 3. What's the drawback of a footless domino? Overfooted. What's the drawback of a footless domino over footed domino? Even if the moment inputs are present, discharge can happen. It need not wait for the clock. It need not wait for the clock. So discharge is not in your control. As and when the inputs are arrived, discharge can happen. So this is something which is beyond your control. You have more control in a footed domino. We have more control, user control in a footed domino gate, which is more robust. Okay. Now if this is so, if I apply the same expression now to a say domino gates, minimum delay condition. Because every gate is now a combination of 2 gates. So now you can apply the same expressions. May I give you this as an exercise? It's given in the book. Everybody has that book, I. Sutherland, Logical Effort by I. Sutherland. So it is given in that, but the derivation is not there. May I leave this? Let us discuss it in the next class. Okay? All of you should try, do the derivations and then come up with the results. Come up with the results. So best stage effort he is getting, which is a function of G and P, he is writing it as G times rho 1 P by G. Why is this? He is making this transformation. Why is he making this transformation? Rho is the best stage effort. Remember, for any G and any P, he is converting it for G equal to 1. He is expressing the best stage effort for any G and any P to G times rho of that gate for which G is 1. And the parasitic is P by G. It helps in making comparisons with the standard static CMOS, which has a G equal to 1. Which has a G equal to 1. It makes it easier. So I request you all to look at this, which is given in I. Sutherland. You can refer the book and then come to this expression. Some kind of those who have done optimizations or numerical analysis, they may be able to do it. I want you to get me the answers. Full derivation. Go, students. Ready for it?
Yes, ma'am. We'll try.
Okay. For domino. Everybody will try to get this expression. So best stage effort you have to get for domino gates. Okay. And once we get that, then it can be plotted. then it can be block. The same value, but now you will not do it for PINV equal to 1. You will do it for P value to be equal to P value. Okay? Then you can compare your result with that of a static CMOS. Very easy. Okay? So this we will do next time. I hope there is some time left. Other period is over. Over. Okay. So we will continue with this. Okay? I have some literature on me on how to apply logical effort to past transfer, but I myself have some confusions over there. So I don't know whether I would be able to take it up. So in case I am not going to take up that topic, because unless I feel confident, I cannot present it in the class. Okay, maybe I can pass it over to you. That will not be a part of your course, but it is just for your general review. If you feel interested, you may go through how to apply logical effort concepts to fast transfer logic. Okay, so this will finish once I think we need one more class, and then we will finish up with the logical effort concepts. So we have more or less discussed everything related to a synchronous system design. We have seen how to design a flip-flop, how to design a synchronizer, how to design a clock distribution network, how to design a PLL, how to design or minimize a combination logical block using logical effort concepts, including the power estimation concepts also. And what else we have done? Anything that I have left? Signaling, wires also. Okay, so now we have seen that what are the design issues which can cause a system or a synchronous system, a pipeline system, or asynchronous logic system, a pipeline system to fail, and how to design each and every block of a pipeline system. So next my task will be to, so this we have done at the implementation level. So next we will move on to the architectural level. Okay, so architectural wise, how to choose the values or the design so as to have an impact on the performance. So my target will be more on the coding or the digital data coding techniques. That's a redundant data coding, and then we will look at the two major blocks: addition and multiplication algorithms. Okay, I hope you all are working with your asynchronous second design assignment. You all have started working with your second design assignment.